Slide is visible, right? ಕಾಣಿಸ್ತಾ ಇದೆಯಲ್ಲ slide?
Yes, ma'am.
Okay. So in the last class, I completed the testing and analysis in the software process. That is the fourth chapter of fourth module, right? So here in the fourth module, you can see here the three major topics are there: test execution, process framework, planning and monitoring the process. I completed test execution and the process framework. One more topic is there, planning and monitoring the process, that I'm going to complete after the completion of module 5, because next week you're having the third test, right? For the third test I'm going to keep the fourth module as well as the fifth module. For that I have to complete at least one chapter of the fifth module. That's why I'm going to start the fifth module today. So in the fifth module, once again you're having the two main topics. One is the integration and component based software testing, and second one is levels of testing, integration testing. So there are two chapters from textbook 2. Those are chapter number 21 and 22. And for the this levels of testing, integration testing, there are two chapters, 12 and 13 from the textbook 1. So first I'll complete the chapters 21 and 22, then I'll move back to module 4. Okay, so from module 5 I'm going to complete two chapters which are related to integration and component based testing. Okay, so these two chapters are taken from the second textbook, that is Marofezi, Michael Ang, that is software testing and analysis process principles and techniques, Village India 2009, same textbook. So most of the chapters are covered from this textbook only. So today I'll start with the integration testing, and after that we'll move on to the component based testing. So it is the integration and component based software testing. So in this, you are going to study about the major integration testing strategies, including the increasingly important problem of testing integration with commercial off-the-shelf components, libraries, and the frameworks. And so why we are going for the integration techniques? Because the problems arise in the integration even of well designed modules and the components. And majorly or importantly, the integration testing is aiming to uncover the interaction and compatibility problems, and we are going to identify or detect those problems as early as possible. Why we are concentrating on detecting those problems as early as possible? Because once we detected, we can solve those problems as early as possible, so that the cost required to solve that will be minimum. Okay, for that purpose we are identifying the interaction and compatibility problems as early as possible. So in this chapter you are going to study about integration testing strategies. So we'll see the overview of integration testing. So to study the integration testing, so first you need to know what is the V model. So or what it consisting of. The traditional V model divides the testing into four main levels of granularity. One is the model, second one is the integration, third one is the system, and fourth one is the acceptance test. So here we are dividing the V model into four levels of granularity. Those are module, integration, system, and acceptance test. So first we'll see what is a module test, then we'll move on to the integration test, system test, and the acceptance test. So first we'll see the module or the unit test. So module or the unit test checks the module behavior or the unit behavior against the given specifications or the expectations. Understood? So the module or the unit test checks the module behavior or the unit behavior against the specifications or the expectations. Then integration test checks the module compatibility, whereas the system and acceptance test checks the behavior of the whole system with respect to the specifications and user needs. Understood? So here we have four different types of testing: module testing, integration testing, system testing, and the acceptance testing. The module test is also called as the unit test. It checks the module behavior against the given specifications or the expectations. Next, the integration test again checks the compatibility of the module, whereas the system and acceptance test checks the behavior of the whole system with respect to the specifications and user needs. Okay, so these are the four different types of testing. Also, here we are only concentrating on the integration testing in this chapter. We are not mainly deal with the model testing system or acceptance testing. We are dealing with the integration testing, and in the next chapter, we are going to study about the component based testing. Okay. So what is an integration test or how it is built? An integration test is built on a foundation of thorough module testing and inspection. Okay, how it is done? Okay, the integration module is built on a foundation of thorough module testing and the inspection. Then module test that maximizes controllability and observability of an individual unit. So as I explained in the in the previous slide, in this slide, or I explained that module test, integration test, system test, and acceptance test, right? And how these test cases are, how these tests are built. So integration test is built on the foundation of thorough module testing and inspection, whereas the module test maximizes the controllability and observability of an individual unit. Here, the integration testing acts as a process check on module testing. Okay, please listen carefully. Integration test is acting as a process check on the module testing. That is, for example, faults revealed or detected during the integration test can be taken as a signal of unsatisfactory unit testing. So here, when we are performing the unit testing or the module testing, what is the main purpose of testing? Identifying the faults or errors which are occurred during each stage of the software development, right? So here by using the unit testing or the integration testing, we are identifying the faults. Then these faults revealed during the integration test can be taken as a signal of unsatisfactory unit testing. Because see here, when the faults occurs means it indicates that the system will not work in a correct manner. So it leads to the unsatisfactory or wrong output, right? So hence we'll treat, once the faults are detected, then we'll treat it as a unsatisfactory unit testing. So one more example is given here. In 2004, a buffer overflow vulnerability in a single widely used library for reading the portable network graphics files are caused security vulnerabilities in Windows, Linux, and Mac operating system web browsers, and also for the email clients. So here the problem is just the buffer overflow vulnerability, okay, which is occurred in a widely used library, that is the portable network graphics. Okay, and then the problem arises in the Windows, Linux, and Mac operating system web browsers, and also in the email clients. Okay, so here once it is detected, or once the fault is detected, then we'll say that the system is not working according to the given expectations. Next, we'll see the some intended side effects of module faults that become an apparent in the integration test, and even a module that satisfies its interface specification may be incompatible. Why? Because of errors introduced in design decomposition. And hence, in the integration testing, we are focusing on checking the compatibility between the module interfaces. Oh, thank you. Okay, so here the integration test focuses on checking the compatibility between the module interfaces. So basically, we are concentrating on the testing. So, integration testing. Integration testing focuses on the checking the compatibility between the module interfaces. See here, the unit test checks the module behavior, whereas the integration test checks the module compatibility. So integration test focus on checking the compatibility between the module interfaces. And when the integration faults are detected or when the integration faults are caused, integration faults are caused by incomplete specifications. Okay, when we are getting the integration faults are caused due to the incomplete specifications or faulty implementations of interfaces, resource usages, are the required properties. Okay, understood? So when the fault occurs or when the integration fault occurs due to the incomplete specifications or faulty implementations of the interfaces, resources usage, are the required properties. And it is very difficult or it may be the not the cost effective to anticipate and completely specify all module interactions, because if you consider the entire project, n number of modules will exist, and then defining the interactions between the models is very difficult, or it is a tedious task, and it is very difficult to anticipate, and it is also a not cost effective one to completely specify all the module interactions, because the entire project consisting of large number of modules, or we can say n number of modules, and defining the interactions between these modules is a tedious task, or it is a complex task, we can say. So next we'll see the different integration faults and what are the examples for the integration faults. So first one is the inconsistent interpretation of parameters or the values, and each model's interpretation may be reasonable but they are incompatible. So the example for this is the unit mismatch, a mix of metric and British measures. So for example, if you consider the metric as the normally in India we are using the meters, kilometers, etc. Right? But in the British measurements, they are using the yards. Then what? Creating the compatibility between these metrics is a difficult task because they are not incompatible, right? Meters and yards, they are not equal. Meter is having its own value, whereas yard is having its own value, so they are not equal. If they are not equal, then we need to bring the compatibility between the metrics. So this is one example. Next one is violations of value domains or capacity or size limit, implicit assumptions and ranges of values or sizes. So one best example for this is the buffer overflow. So in the previous slide, you have seen that here in 2004, a buffer overflow exists. So that causes the vulnerability in the Windows, Linux, Mac operating system web browsers, right? Similarly, here also a buffer overflow in which an implicit or unchecked capacity bound imposed by one module is violated by another one. So if we consider the different versions of the web browsers, so because nowadays we are getting number of versions of web browsers, each day the version number changes. Then if they are not compatible, then the problem arises. See here, one problem is in some versions of the Apache 2 web server, between these two versions, that is 2.0.35 and 2.0.50, could overflow a buffer while expanding environment variables during the configuration file parsing. So then what happens? So since these two versions are not compatible, then the buffer overflow occurs. When the buffer flow occurs, then there is no compatibility. If there is no compatibility, then the problem arises. Next one is side effects on parameters and resources. The example for this is as we know that a module uses the resources that are not explicitly mentioned in its interface. So then the integration problem arises when these implicit effects of one module interfere with those of another module. The example is using a temporary file TMP. It may be invisible until the integration with another module that also attempts to use a temporary file TMP in the same directory of scratch files. So best example, when you are using or when you are writing the problems by using the temp, then accessing that by two or more procedures or by two or more programs, then the problem arises. But before that, that is not visible to the user or to the programmer. So this is one type of integration fault or integration error, that is side effects on parameters or resources. Next one is missing or misunderstood functionality. Under specifications of functionality may lead to incorrect assumptions about expected results. Here the counting it's on websites may be done in many different ways. Per unique IP address or per it including or excluding spiders and so on. So for example, when you're browsing a particular website, there you can see the number of hits. Then how we can consider the number of hits or for how many times that website is opened or used. So that depends once again based on the unique IP address or per read. So if different users uses the different methods, see let us consider that one user requires for the unique IP address or the other user requires for per read or by including the spider etc. Then the problem arises because if problem arises if the interpretation assumed in the counting module differs from that of its clients. Okay, so this is another type of fault. Next comes the non-functional problems. So in the non-functional properties, like the performance are typically specified explicitly only when they are expected to be an issue. All right. So even then the performance is not explicitly specified, we expect that the software providers results in a reasonable time. So because the interface between the modules may reduce the performance below an acceptable threshold. Because here as I said, in a project, we have the number of models exist. Then, if there is a problem with the interference between the models, then it reduces the performance of the system below some threshold value. Then the problem arises, and that particular fault is called as a non-functional problem. Next comes the dynamic mismatches. Many languages and programs allow for dynamic binding. Problems may be caused by failures in matching when modules are integrated. The example is polymorphic calls may be dynamically bound to incomplete methods. Because see here, if you are using the C or C++ or the Java, then some frameworks allow the or some languages allow the dynamic binding, where some other languages are not allowing the dynamic binding, then the problem arises. Okay. So these are about the different types of integration faults and the example for each integration fault. This, we will see in terms of the software problems, and the integration problems may be attacked at many levels. Attacked at many levels means, as you know, that in the software development process, many levels are there, are many phases we have to pass through, right? So starting from the requirement collection, requirement specification, design and development, finally integration, right? And these integration problems may be attacked at many levels. So integration problem may be exist at the design phase itself or during the development stage. Okay, and good design and programming practice and suitable choice of the programming environment can reduce the some integration problems. Okay, so as we know that the integration problem may occur at different stages of software development, and by properly choosing the good programming environment and by choosing a good design and programming practice, and by choosing the proper programming environment, we can try to minimize the classes of integration problems, or we can minimize or reduce, or even to some extent we can eliminate some classes of integration problems. For example, if you consider in the application demanding management of complex shared structures, choosing a language with automatic storage management and garbage collection greatly reduces memory disposal errors such as dangling pointers and redundant deallocations. So here, if you consider in case of the memory management system, and if we choose the automatic storage management and garbage collection, then this reduces the memory disposal errors such as the dangling pointers and redundant deallocations, because there we're using the double freeze. Okay. Next, we'll move on to the, even if the programming language choice is determined by other factors, many errors can be avoided by choosing the patterns and enforcing coding standards. Coding standards means if we have a standard, what we can say, algorithm, and that algorithm can be implemented by using any programming languages. So here the main thing is whatever may be the programming language the developer can use, but by using the patterns and enforcing the coding standards across the entire code base, then we can avoid the integration faults or integration errors, because we're using the standards that can be designed in such a way that violations can be easily detected manually or by using the automatic tools. So one best example is when we're using a C or C++, it requires the use of safe alternatives to unchecked procedures for such as requiring the string copy or string length CPY or in place of string copy. See here, string copy is there. Along with that, we are requiring the strncpy, string in copy or string in copy. Then so when we're using these two in place of the string copy, then we have to check which type of parameter or which type of procedure is used. So there we are using the safe alternative method in order to avoid the faults. Next one is checking for the mere presence of string copy is much easier than checking for its safe use, because see here, once it is used, it depends on the programmer or the developer how he is using. If he is wrongly using that particular procedure, then may it leads to the failure of the program. Right, but rather than checking the safe usage, we can check for the presence of that procedure. That is, we can check for the presence of string copy. Then these measures do not eliminate the possibility of error, but integration testing is more effective when focused on finding faults that slip through these design measures. Next, we'll move on to the one more topic called as integration and testing strategies. So integration testing proceeds incrementally with assembly of modules into successive layer subsystems. So basically integration means what? Integration means combining, right? So here if you are applying it to the software development, so as we know that entire software product is divided into number of modules, and each module is independently designed and developed. Or once each module is implemented, finally we are combining or integrating all the modules together. Okay, so then once we combined all the modules, along with that or parallelly we are checking the working of the system, and that is called as integration testing. Okay, what is integration testing? Integration testing proceeds incrementally with the assembly of models or with incrementally with combining of modules into successively larger subsystems. And why we are preferring the incremental testing? We are preferring the incremental testing to provide the earliest possible feedback on integration problems, because if we are performing the integration testing at last means after the system is implemented, then you are going for integration testing, then more problem arises. But if you to identify the incremental problems or to identify the integration problems at the earlier stages itself, we are using the incremental testing. Understood? So to identify or to check the uh, faults such as the integration problems, we are using the incremental testing. Next one is controlling and observing the behavior. Controlling and observing the behavior of an integrated collection of modules. Are you there in the class? You are listening, right? Are you following my presentation? Yes?
Yes, ma'am.
Okay. So we are looking into the integration testing strategies, right? So next one is controlling and observing the behavior of an integration. Is controlling and observing the behavior of an integrated collection of modules grows in complexity with the number of modules. As I said, in the system we have n number of modules. If the software system consisting of only two modules, then integration of those modules is easier. If the software product consisting of 10 modules, let us say, then also the combining or integration of those modules is a simpler one. But if you consider the software system which consisting of thousands of modules, okay, thousands of modules, if we are combining together, then the complexity increases, right? As the number of modules increases, the complexity also increases. Understood? That is the meaning here. As the collection of module grows in the complexity with the number of modules and also with the interaction increases. Okay. So hence we have to control and observe the behavior of an integrated collection of modules. So for each module we have to observe the behavior, or we have to observe the behavior of each module in order to avoid the complexity and as well as to avoid the complexity in the interaction. Here, because the complex interactions may hide the faults. So once the faults are hidden, okay, then these faults may exhibit during the end stage. Then identifying such faults and the correction of those faults may leads to the more cost, right? So hence, we to minimize the cost, we have to identify the faults at the earlier stages itself. So complex interactions may hide faults and failures that are manifested, may propagate across many modules, may take the fault localization difficult. Hence, it is worthwhile to thoroughly test a small collection of modules before adding more. Means, so test the module one by one, then combine two modules, then test the system once again and combine three modules, because we have to go in a manner. So we have to incrementally we have to combine or integrate the module together. So before integrating the modules, we have to check the working of each module, then combine two modules, then check the working of that module, then combine three modules, then check the working, like that. So this procedure we have to do it incrementally, because if you are combining all the modules together at a time, and if one of the module is not working, then it may affect the entire system. So to avoid that, we have to perform the module testing in an incremental manner. Because incremental assemblies of modules are incomplete without construct scaffolding, driver steps, and various kinds of instrumentation to effectively test them. Because here in the incremental testing or incremental thing, we are not only combining the models, along with that we are also using the scaffolding, means it consisting of driver steps and various kinds of instrumentation. That hence we need to consider all these components together when we are performing the module testing. So one approach to avoid the cost of scaffolding is by waiting until all modules are integrated and testing them together. But so then that may leads to the undetected faults. Okay. But if we are mainly concentrating on avoidance of the cost or minimizing the cost, then we have to perform the scaffolding when and by waiting until all the modules are integrated and tested. Then we are using the scaffolding, then the cost of scaffolding will be minimum, right? But in this Big Bang approach, neither steps are not drivers need be constructed, nor must be development be carefully planned to expose well specified interfaces to each subsystem. So it's very difficult at the task, because for each module defining the steps or the drivers, it's very difficult. And the savings are more than offset by losses in observability, diagnosability, and feedback. Because it's okay, by using some techniques you are minimizing the cost, but that may lead to the more number of or more number of failures, then the saving is not the purpose of saving is not served. Right. Next, delaying the integration testing hides the faults whose effects do not always propagate outward to visible failures. Because see, you're violating the principle that failing always is better than failing sometimes, and impedes false localization and diagnosis because the failures that are visible may be far removed from their causes. And what is our requirement is we require the whole system to be available before integration does not allow the early test and feedback, so that the faults that are detected are much more costlier to repair, because here we are performing the testing after the entire system is ready, or after the all the modules are integrated together. And in that case, if the faults are detected, then correcting those faults are costlier. Okay, or we require more cost and time to repair such faults. So hence, the Big Bang integration testing strategy is less rational strategy than to attempt to recover from a lack of planning. So it is therefore also known as the desperate tester strategy. Okay, so Big Bang strategy is also known as desperate tester strategy. Why? Because in Big Bang integration testing, we are performing the testing at the end. At the end means once the all the modules are implemented and they are combined together, then only we are testing for the faults. But once the faults are during detected during that stage, then repairing those faults is a costlier one, and hence the Big Bang integration testing technique is also called as desperate testing technique. So one example is the memory leaks that are typical of program faults that often escape the module testing. They may be detected in the integration testing, but they escape further and are discovered only in the actual system operation. Okay, so this is the major problem. Memory leaks when we are using the different memory management techniques, then the faults occurs. Then if those faults are not detected at the earlier stages because they escaped from the testing, and these memory leaks will occur during the actual system operation, then the problem arises. One example here you are given web page reports that arrived on the secure server port. So for this, then the when we are using the pointers and the memory operations, then the problem arises. Because here, if you consider this code, the fault is nearly impossible to see. Just by seeing the code, you cannot identify where the fault occurs, right? So the memory that should be deallocated here is a part of the structure defined and created elsewhere in the secured socket layer subsystems, and which is written and maintained by a different set of developers. Because here, whenever we are using the secured socket layer, see here we are using the SSL, that is the secured socket layer, and if it is the secured socket layer subsystem, whereas this one is written and maintained by a different set of developers, then the problem arises. Because reading the definition of the app underscore filter underscore T structure, which occurs in a different part of the Apache web server code, it does not help you, because the CTX field is an opaque pointer, that is type-word pointer in C. So then the repair applied in version 49 of the server is, so here this one is changed. So here if you compare this particular statement with this, here that particular fault is repaired in the version 2.0.49. For incrementally testing partially assembled systems, we have two main classes. One is the structural approach and second one is the future-oriented approach. So in the structural approach, what happens? The modules are constructed, assembled and tested together in an order based on the hierarchical structure in the design. So in the design phase, we have already defined the entire system design, right? It consisting of different modules, and here those modules are constructed, assembled and tested together in an hierarchical manner, which is present in the design itself. So we'll use the structure which is there in the design, and according to that we will combine the different modules. Whereas the structural modules includes the bottom up and top down, and also the combination of these two. Sometimes we are using the sandwich of these two. Okay, so either bottom up is used or the top down is used, but in some of the cases we are using the combination of these two, and it is referred as the sandwich or backbone strategy. And here the future-oriented strategies derive the order of integration from characteristics of the application, and which includes the threads as well as the critical module strategies. And if we see the top-down and bottom-up approaches are the strategies, these strategies are the classic alternatives in system construction and incremental integration testing. Okay, because in the incremental integration testing, all the modules are constructed, assembled, and tested together by following some order which is defined in the design phase. But in the what in the structural approach we are not, sorry, in the feature based approach we will not use that. We'll use either the top down or the bottom up strategies or the combination of these two, and this is the classic alternative to the structural approach. So next we'll see the testing components and assemblies in the next class. Okay, so we'll see the testing and testing components and assemblies in the next class, and also the level of testings. So any doubt in this the topics that we have studied today? Any doubt? How many of you are present today? Three. Suraj, Gaurav Kote and Misbah. Right? What about others?